don't feel obligated. I'm just joking, of course. Don't feel obligated in the slightest to look at this video. If you happen to be interested, please do, etc. Anyway, that's a video that's been watched quite a number of times. Okay, so speaking of relativity, electrodynamics. Electrodynamics has special relativity built into it. We haven't looked at that yet. That will be a couple of lectures away from today. This week we were just doing a recap of how electromagnetism works. And what we did a couple of days ago was that we just went through the experiments, the mathematical conclusions came out of it, and we just rewrote these mathematical conclusions in a number of ways. And all of them are useful for a particular application or situation or problem that you happen to be looking at. So maybe for future reference, because we're going to do a couple of exercises with this. So we just write down what they were. There's sort of a notepad here. It's a black one. So there are 3 of each. For electricity. And I guess you know what these are, right? There's one. This is the, I would say, the easiest to actually find in an experiment. So this is the one that tells you how much electric field there is at a certain position, given that you know how the charge is smeared out over that volume. And really note the notation of the R's. 4 pi epsilon 0. These numbers are just convention. The 4 pi came from the idea that smears out over a sphere and such. The epsilon 0 is a consequence of how we chose our coordinate system. Excuse me, not coordinate system, our unit system. And there was a big R, and it says something about the difference between the point where you happen to be looking, which is R, and the point where this particular piece of charge is, which is R primed. And the integration is over all these R's, right, over all the volume. So you go through the area, through the volume, I have to be technical here. You go through the volume and you pick up where every piece of charge is. Where a piece of charge is called R primed. Then you calculate how far away R primed is from where you are standing. That distance, that vector is called big R. Then you do this integration, it tells you at your position how much electric field there is. That was this equation. And then we rewrote this in at least 2 different forms. One of them was this. That the divergence of the electric field is the same as the charge density divided by this number. And the final one, again, just a rewrite of what we already knew. Same physics, different mathematics. It says that if you have your electric field and you close up a piece of volume in some area, some close-up area, this is what this means, it's a closed-up area, area closed, then what it should give you is how much charge there is within that area. Those were the 3 equations. So there's that. Magnetism, same story, 3 equations. The first was the law of BO supply, that's how we started. Same idea, you want to know how much magnetic field there is at your position R. What you do is, you look at how much current there is flowing at a particular position in space. That particular position in space is called R primed. The current is called J. You take its outer product with the distance between you and that piece of current. That's this one. Outer product divided by the distance squared. Integrate over all volume.
Does that need a half?
Well, not really, but I mean, this is just a distance, it's just a number. And yeah, I guess you're right. It doesn't really need it. So that's this one. That's all the all the physics that we need. The rest is just a mathematical rewrite. 2 different ways. We skipped the mathematical steps for this one. They're not that hard, it just takes a while to get there. But there were 2 different forms. One of them was, help me out here by the way, you have it somewhere?
The cross product.
The cross product of the B field.
Yeah.
Yeah.
Gives us what?
Mu naught.
Exactly. This one is going to be very important for the end of today's lecture, because I would like to end today with the full Maxwell equations. We already have a couple of them right here. You already know what they are, but I just want to show you, after we've done some of the mathematics, to show how they actually follow from the rest. Okay, so by the end of today, we should have the full Maxwell equations. And this is already part of one of them. And this, by the way, is actually one of the Maxwell equations, the first one. Okay, and then there was the last one. Here's the idea. There are some currents floating in this direction. You let it go through a disk, and you want to know how much current is flowing through that disk. And the idea is, well, take that disk, calculate how much magnetic field there is around the circumference of the disk. That number that comes out is equal to how much current has flown through the disk. That was this one. So again, it's a closed integral because you take the full closed circumference, take the B field, the L means over the circumference, and what it gives you is up to a number, mu0, it should give you how much current has flown through it. So these were the three ones. This is part of the fourth Maxwell equation. And I'm leaving it open because in a moment we'll see that there should be some extra term that we haven't found up till now. So this is really just a recap of everything. One small add-on, and then I think we should actually start with the exercises. Given that you have an electric field, you know how to calculate how much force or charge would feel, yes? Because, I mean, the electric field itself doesn't really tell you anything. It only tells you something if you can use that field to calculate how much things are dynamic, or how much things are being pushed away. What was this one? You want to know how and in what direction the charge Q is being pushed. Calculate the electric field by one of these three means. Put it in here, gives you the force. And if you have the force, you can do mechanics. Magnet is the same story. Once you know how much the magnetic field is, you can calculate how much a moving charge is being pushed around. And unfortunately, that equation is somewhat more difficult. You take the velocity of the moving particle, its vector, take the cross product with the magnetic field, and then you multiply it with the charge itself, and this tells you how much the flowing charge is being pushed around. So that's really all recap, I think. Any questions about this? Okay. How did the exercises go? Made some pre-selection, as in why I think these are the most important. Were you able to solve some or all, or pieces of them? If not, that's fine. That's why we're here, of course. I see some people nodding along. I see some people doing the How about we just go through a couple of them. By the way, my personal preference is to have you work on these exercises at home, in your own time, and then we actually put dots on the I here. So we actually do the exercise. Unless people really have a strong preference for sitting here and here trying to do the exercises by themselves. I'm happy with both cases. No? Okay, good. We'll do it like this. My idea is to do a couple of them, the ones that I promoted. 2.9 is a very important one because it teaches you how to use these equations. So I would like to do that one. A very nice follow-up exercise for this one is equation 2.14. They're very much related, and they give you a very good idea of how to work with these equations and doing these crappy integrals with all the vectors and such. So just for a technical exercise, I think that's a good one to look at. Another exercise that I will find extremely important to work on in a moment is the following. One of the mathematical exercises that I sent you was this. That if you take the divergence of a curl, then it should always be 0, regardless of the vector f is. Just to do some expectation management, is there somebody who might know why I just randomly take two of these strange operations and let you calculate why this is 0? Do you happen to know maybe from electromagnetism how this will come into play in our understanding of electrodynamics? mean, it's just a random physical exercise, right? But also randomly asks you, so well, please calculate the antiderivative of the logarithm of the tangent squared. I mean, that's just as random, but there's a reason for this one.
This is about the divergence of the magnetic field.
Yes, actually. Because in a moment, again, this is just expectation management, but in a moment, what I would like to talk to you about is this should be true for all vectors. So that also includes magnetic fields and electric fields. And we will find that once we have the Maxwell equations built up from these, we will find that not all of my electric fields and magnetic fields obey this general mathematical law. Now, that means that physics contradicts mathematics. And typically, then mathematics will win. So that means that the Maxwell equations that we're building up a couple of days ago and some extra ones today are not going to be complete. They don't agree with mathematics yet. We will show in a moment that if you try to apply this rule to your magnetic field, it will not give you zero. And it should. Mathematics should win. In fact, you can already sort of see it here, but we're going to go through this in mathematical detail. But here is a rule, one that we derived. The curl of a magnetic field should give you this. But the divergence of this thing, like every divergence of a curl, should give you zero. Now, if you take the divergence of left-hand side, you also take it on right-hand side, should give you zero. This one does not give you zero. So that means that this rule is not complete, even though we derived it from experiments.
So if you would add that extra term that you just mentioned.
Yes, yes. We're going to add the extra term in order to make this law agree with what mathematics wants it to agree to. That's the idea. So this is why this is an important exercise. So I would like to do this one. And then actually show you what this extra term is, which is going to be very easy once we have it. And then we have some random exercises floating around. Now, before we really start, your good friends at PBay might actually find you a solution manual to the book. I had no trouble finding it at some point when I looked for it. No difficulty whatsoever. That means that if there are exercises that you find particularly difficult and we don't find the time here to work on them, there is a complete solution manual, not just the answers, also step by step how to go through it. So I would really advise you to do that as a self-study guide. There is some danger there, that is that people might, once they know the answer, work their way towards the answer, which is educational, but not as educational that you first don't know what the answer is. So you really have no other means but your own understanding. So advice, if you find this solution manual to work on these exercises for yourselves, the ones that we don't get around to, first try them with the book closed. So you don't fall into the trap of just working your way towards what they've already said that the answer is. Okay. Good plan? Some more people think, well, we should also do this maybe? Yeah? You feel like saying, well, this exercise gave me particular headache, please tell me, we'll just do the real time here. But I'm going to start with exercise 2.9. Now, the exercise is as follows. They tell you, well, there is a situation in which the electric field vector is given by some number, k, times the distance of you to your charge, to the third power, and it points in that direction. Now, I have a hard time envisioning how this could come to pass. Taking just any one of you as my charge. What it says here is that the electric field points between us, points outward, but it also says that the further I get away, the stronger the field gets. So I'm not sure how physical this situation is. But apparently it is. But then again, they never specified that it's only one charge. It might be some other charges around in the vicinity that make it such. Right? They don't make the distinction. We're going to accept this as a fact. And then the question is twofold. One of them is calculate the charge density. Suggestions?
Well, at least use, was it the second one as well?
Yeah. Yeah. I guess so, right? You have three equations that relate charges or charge densities to the electric field. And as we've discussed many times now, it's just a matter of finding which one is the most appropriate for our situation at hand. And yes, that will be that second one, the one that we call the first Maxwell equation. So yeah, we're just going to plug it in. Okay. Use the first Maxwell equation. So there we go. We have to take the divergence of this given electric field, and what it gives us back is exactly the charge density that we're looking for, well, except maybe for an epsilon zero. So let's write it here. The outcome should be exactly what we're looking for. We run into trouble immediately, unfortunately, because here's the divergence, and I hope if you were not too familiar with it that you've looked it up exactly what it means. But a divergence typically is take the x derivative of the x component of E, the y1 and the z1, add them all together. But our electric field is not written in x, y, and z coordinates. It's written in distance coordinates. So that means our coordinates of our divergence and the thing that we have to take the divergence of are not the same type of coordinates. So we have to rewrite one of them in terms of the other first. That's the idea. Now, fortunately, mathematics does not care which one you do. We can either rewrite this given expression into x, y, z coordinates, and then take the divergence as is, or we leave it in these spherical coordinates, these radial coordinates, and rewrite the divergence into radial coordinates. Both of them work, of course. I would do it in spherical, for the simple reason that the situation is extremely spherical. I mean, the whole setup from the start is spherical. I mean, you're of course, you're very happy to write it into x, y, z, then calculate this. But x, y, z coordinates are just so crappy. Right? I mean, if these are the x, y, z coordinates, this is x, this is y, this is z, and then you happen to be the point of origin or something like that. If I just walk away from you in a radial line, this will give me immediately how strong my electric field is at some point. However, if I do the same radial walking, then I see that my x is changing and my y is changing, so it becomes this complicated mess. So might as well do it in coordinates, in spherical coordinates. So that means this one we have to rewrite in terms of spherical coordinates. Just out of interest, have you ever done this before, maybe at some mathematics course?
No, I don't think so.
Well,
We might have.
Yeah, I think
Was it a mathematical science?
Do we?
I don't think so.
We did polar
But in the
coordinates.
book they talked about,
Yeah,
but not
we,
the divergence of
Yeah, exactly. We
spherical
did the
coordinates.
divergence and polar coordinates,
but not
I see.
That's where I was stuck.
Okay. Well, the good thing about these sorts of exercises is you only have to do them once to convince yourself that the actual expression that comes out is true, and then for the rest of your life just use that expression. By the way, here's another reason why it pays to rewrite that divergence into spherical coordinates, because that means that you have to only do it once and you can apply it every single time for next exercise. Whereas if we would have kept this x, y, z and have rewritten this for every new radial exercise, we would have to rewrite our E field into this new coordinate every time. Let's do this one. Now we're not going to do the full exercise. It's not that hard, by the way, to rewrite it in spherical coordinates. It just takes a lot of time. If you happen to have found a copy of the book, in the front cover they give you the expressions. Now, you don't need this book to give you that expression. It's written in all books on vector calculus, and open up any random web page, it probably starts with this one. So we're just going to copy paste that one. Now, I'm going to give it to you. I never know this one by heart. I always have to look it up what it is. But it goes like this. You have a random vector, V. And you have to take its divergence and you do it in spherical coordinates. And the outcome, unfortunately, is a somewhat involved expression, but it will simplify enormously in our particular case. Let me just write it down. correct. Now, to give some idea of what this means, any point in space, of course, you can designate not just by the x and the y and z coordinates. You can also just say, well, from a particular origin, it's this angle in that direction, this angle in upward direction, and this many meters from the origin. Those are these coordinates. And you can easily, by your laws of sines and cosines, relate your x, y, and z to the angles. Right? This is a basic exercise in mathematics. That if you know that this is your x angle, and this is your y angle, and you know that this y angle is just the radius times the cosine of the angle. And your x coordinate is just the radius times the sine of the angle. Now that means that you can relate x's and y's to angles and to r's, to radial distances. And from that moment on, it's really just rewriting all your derivatives, which are here in x, y, z, into derivatives of the angles and the radius. And that's just a basic exercise in mathematics, right? By the chain rule of differentiation. But you can imagine that it takes a while because you have all these trigonometric identities that you have to work with. So this one, we're not doing it. I'm just giving you that this is the answer. One final comment. Vr, v theta, and v phi mean the three coordinates of this vector v, but now in r, phi, and theta direction. So this one is how many angles it is in theta. This is how many there is in phi. And this is how many there is in meters. That's the idea. Now you can immediately tell in this particular case that these are going to be 0. Because r, v, e vector, does not depend on the angles. So this one is 0, that one is 0. So it all boils down to 1 over r squared. The derivative with respect to r times r squared times r vector, but only the part of the vector that points in r direction. That's the whole expression. So that will be give us k times r to the 3, and we would have this. I hope you understand that the r hat is gone.
I didn't understand the last step.
The
So we replace
parentheses.
e by
Yes,
1.
by the whole expression.
Okay.
And the reason is that our divergence in spherical coordinates asks here for how much of the E field is pointing in r direction, and that's all of it here. In our
So we just
situation.
take the first argument, we don't look at the,
Yes.
the other angles.
Yes, because this one will take the derivative of our vector with respect to theta, but there's no theta there, so it will be 0.
Oh, okay, yeah.
And there we go. And the same thing with phi. So it becomes very simple. And the r hat is gone. Right? R hat just means the part of E that sticks in r direction. Well, that's all of it in this case. Alright. So that gives us 1 over r squared. Derivative of r with respect to r of k. Or can take the k out of the differentiation. R to the 5th. And I'm sure we should be able to work out what this is. Epsilon k r squared 5 times r to the 4th. This is correct, yes? Some things drop out. This is 5 times epsilon k r squared. There we go. So that's the answer. The charge density is some number that increases with r squared. That's the answer.
It still doesn't make sense.
What part?
The density increases if distance increases.
Oh,
Or doesn't, like, to me it doesn't make sense.
well, it doesn't make sense if we just assume that there's only a piece of charge over here. Then walking away, of course, should not increase the charge density. But apparently what we find here is that we have set up some sort of jelly, maybe. And part of this jelly is connected to a Van Graaf generator that makes pluses, the other one makes minuses, and apparently the amount of pluses increases more than the minuses do, something like that. So as you walk towards the pluses part, you increase the amount, something like this. No, but you're right. I mean, if this were just one particular piece of charge, or a smeared out piece of charge but only over there, and the rest is vacuum, yeah, then this won't hold. The more you get away, the less it will become the charge density anti-electric field. But apparently there's also charge behind me. This is why I say there's some continuous jelly with some strange distribution of charges in there. But here it is. So that's 2.9 exercise A. Only difficulty here was understanding that you got something in radial coordinates and you had to, and the derivative was with respect to Cartesian coordinates, that you had to do some rewriting. That was all the difficulty here. The rest is just plugging in, doing the mathematics. Alright, so that's good. Exercise B.
Is there a part B to it as well?
Oh,
sorry,
yes,
yeah, sorry.
yes, just about to start, yeah. The part B is, okay, well, how much charge is there? We have a charge density, so we should be able to find out how much charge is there. And I think they talk about, you take this jelly with this strange combination of charges everywhere. You take a sphere of that thing, how much charge is there within that sphere? That's the exercise, yes? Okay. Well, we need charge. I like this idea. This is completely filled with some sort of jelly. We're plowing through that, walking towards charges, away from some other charges. The question is, we now take this one sphere of that stuff. How much charge is within that? Suggestions, how to calculate this?
Where do we go? Yeah. Use the third.
The third one. Yeah, because this is what we need, right? The enclosed charge. This was the idea. You take a piece of volume, you take how much area is around this, calculate how much electric field is there on the area, and the answer tells you how much charge there was inside. The enclosed amount of charge. That's one way, by the way. There's a second way too. Because the amount of charge in total is just the charge density integrated over the volume, right? And now this one requires us to use E. Well, we happen to have that. So this one we can use in the third equation. But now we have this one, we can also just integrate this one over the volume of that sphere and also get an answer. It should give us the same answer, so it's a good sanity check. So let's do both. Now, conceptually, I think this one is the easiest.
Yeah.
Amount of charge per unit volume, integrate over the volume. Let's see what we get out. The amount of charge in a sphere of radius capital R, just by definition of what this thing means, charge density should be the volume integral of the charge density. And let's put in immediately the charge density we just calculated is 5 epsilon 0 k times r squared. And over here. Let's continue from here.
Well, you need to get it in terms of, you need to get the V in terms of R, right?
Yes.
So you want to rewrite that as, I had 4 pi R squared,
Yes.
right? And then it becomes dr.
That's true.
But then you also need to set the boundaries to,
Yes.
well, R.
Well, this was the integrand, the original one. And the dV, if you want to know how much volume there is, what you could do is just take, you were right, I'm just going to hopefully visualize a little bit how you can get the amount of space in the sphere. What you could do, you could just say, well, let's take the area of the sphere, and then on top of that, make a somewhat bigger sphere with its own area. Then the amount of extra stuff that you put on there is the increase in volume. So increase in volume in case of spheres just means putting extra layers on top of that sphere. At some point, if you have enough layers, you will get a bigger sphere. And the amount of extra stuff that you put in there is just the sum of all the areas that you put on top. And that was your suggestion. Instead of integrating over the volume, you can say, well, let's just integrate over the area of the thing, and then increasingly do so. Put more and more of that area on top of the other one. One way of saying, of visualizing this maybe, so that's this. One way of visualizing this is like this, right? That if you have this tennis ball, you paint it blue or something like that, You put a layer of blue on top of that, that will cost you 4 pi r squared amount of blue paint. But because the paint has a certain thickness, your tennis ball has become a little bit bigger. You do it again, another layer on top, gives you some more volume in the thing. How much more? Well, the second layer of paint that you put on there. You just do that as long as you want, and at some point you will get this huge, big blue ball with this small tennis ball in the middle, and the rest is just this big paint ball, but this is the idea. So that's what we do here. VV is really just that thing. And now we are in familiar territory, because now we can do this integration. And you're right, we have to specify. Our tennis ball here begins at radius 0, and we put on paint until it has radius big R. This, of course, is just first year calculus. How to solve this? 5 epsilon 0. Okay, there's another 4 pi there. 1 R. R to the 4th. The R just got all the constants outside. Antiderivative, put in the boundaries. This will give us 0, this will just give us big R, the 5's will drop out. 4 pi epsilon 0 k R to the 5th. And that will be the amount. Is that completely true? I'm not missing an epsilon 0 somewhere? No. Oh no, of course. No. I was looking at this equation here. This one, we never used this one. We just put blue paint on balls. That's what we did. I'm sure this is, well, no, let's not go there. This is the expression. So in principle, we're done. I'm sure I haven't looked at how the book does it, but I'm sure the book wanted us to use this one instead. Well, so there's a set.
That you can solve it with 2 different ways.
Yeah, it says.
Oh,
to
it
do
actually
two
explicitly
different
says?
ways.
Okay. Okay, there's probably the 2 ways that they mean, yeah.
Yeah.
Alright, well, let's do the other one. Make some room here. Use that law, so the closed integral of the electric field vector should equal the amount of charge enclosed divided by epsilon 0. Okay, well, let's plug in our electric field. Or the epsilon 0 will go here. There we go. Okay, epsilon 0. I'm going to put in the k's and such. K R to the 3rd. R hat. This is the integral that we have to solve here.
Yeah, so you just rewrite. Was it area in terms of R?
Yes.
Which is 4 pi r squared. Is it? Wait. Yeah, it is, right?
What is what exactly? For
Yeah, 4 pi r squared. But then no, wait. Sorry, I'm confusing myself.
I sure understand what I think that you want to do is rewrite the dA as a dr.
Yeah.
So you can do the integration.
Yeah.
That happens to be wrong. We can do the mathematics, but it's physically wrong. It's not. We're doing a different type of calculation than what we want to do. But let me just.
Oh, is it because it's a surface integral, not a normal integral?
Well, in short, the answer to that question is yes, because we're integrating over a sphere, and you want to rewrite it as an integration over R, as if we're making the sphere bigger and bigger and bigger. We're not making spheres bigger.
Yeah.
We just have a sphere with a fixed R.
Yeah.
But wait. If we have a fixed R, which happens to be capital R, this one, then that means that these R's are all just constants. Epsilon 0 k R to the 3rd. I've already got it out of the integration. And the only thing that remains really is this.
Yeah.
And it's not this is just calculating what the area is of a sphere.
Yeah.
Why did you change
Yeah.
the small r into the big R then?
Oh, because the area on which we are looking, right? That's what this formula wants us to do. Well, it tells us to look at a sphere or some closed-off area. Look how much electric field there is at any position. But the exercise says do it at distance r, a fixed distance r. So we're not increasing r's. So that means that this one is really just big R, gets outside of the integral. What remains is just the integration over the surface of the sphere. And to be honest, when I first did this exercise, I also fell into this trap that I thought, oh wait, I can rewrite a dA in terms of a dr. And then I realized, wait a minute. First of all, I didn't get this answer, so I knew that something was up. But secondly, then I realized it's physically not what we're doing. We're not increasing this tennis ball, putting layers on top. That's not what we're doing in this exercise. Okay, but this now is easy, yes? Epsilon 0 k r to the third times the surface of the ball with a fixed distance, radius, 4 pi r squared. Gives us 4 epsilon 0, 4 pi epsilon 0 k r to the fifth. That's exactly what we have here. So there we go. So there's that. But yes, I mean it's a very easy trap to fall into. For mathematical reasons, we tend, if we have seen integration that we don't like, integration variable, just rewrite this integration variable that we do like. And we don't always really necessarily understand that we might be changing the actual thing that we're doing physically. So, well, it's a good sanity check. So, advice if you make exercise about these things and you find you can do something in two different ways, it's sometimes wise to actually try to do both ways, just to see if you get the same answer. Final comment about this exercise. I think we can now better understand how this jelly, this charge density is actually charged. Because apparently the further away if you take a sphere of this, the bigger you make the sphere, the more charge is in there. It goes up to fifth power, so it increases enormously. But then I sort of understand. If I have this amount of charge here, and I just make sure that there's more and more charge as I go to the outside, then it's also understandable that if I make a bigger sphere, I am including more and more charge that increases more than the actual sphere increases.
Wait, can you say that again?
Sure. Jelly, origin, I have some charge here.
Yeah.
And as I move out, apparently, and I integrate over all the amount of charge that's in there, charge density, I get a bigger number as I get bigger. But if it were evenly distributed, it would have gone like r to the third. Because a volume of this jelly, the volume itself, goes with r to the third. Now, the fact that I increase the volume by r to the third, but I get r to the fifth more charge, means that there's more charge at the outer edges.
Oh, that's what, yeah. Okay.
So apparently you can really set this up. Just make sure that you have a small amount of charge here, and you make this big Van de Graaff generator around your room that piles up charges from the outside. Then you would probably get something like this. Okay, any questions about this? What do you think is the best take-home message maybe for this exercise? I mean, it's not so much the actual formula that comes out, right? But suppose you encounter this next exercise about electric fields. Something you pick up from this exercise that might be useful? Morale to the story, maybe?
I guess just there is different ways of looking at it, at the physical situation. Yeah. Yeah, I don't know. Like if it wouldn't have told me to actually do it that way, then I would have done this way.
Yes.
And then yeah, not have understood. what that one actually does. So, yeah.
Well, that touches on one of the morals of the story, I think. I'm just repeating myself. Make sure that if you change integration, that you're not changing your physics, because that's what we originally did. Secondly, there's indeed multiple ways of doing the same exercise, and that you can use in your benefit, that you can cross-check whether your previous answer was correct. Thirdly, if you find yourself in a situation where your divergences and curls and such do not match up in coordinates as your setup, you have to change one of these, and I advise always change these, because those have been worked out for all situations, whereas this one you would have to change for every new situation. So there's that. How about we try another electrical exercise? The idea is exercise 213 that I would like to do. I love this one. If you have the book in front of you, maybe it's a good idea to read the exercise so I can screen the board. Thank you. But, I always think that this is a mouse.
Yeah.
Yeah. I'm going to leave this. So all seen the exercise? This is draw a thing. Exercise 13 is as follows. The following setup. You have a wire. And we would like to know how much electric field there is. A distance S from the wire. Thank you. Now the wire does not carry current. So there's no I. There is charge though. There's electrons in the wire. It just happens to be that the electrons are not moving. If the electrons were moving, you would know that there was also a magnetic field, and that one we have already calculated 2 days ago. So it's really the same exercise. It's just now for stationary charges. So that means you will get an electric field. Just the test question in the previous exercise with the magnetic field. Where was the electric field there? Was there an electric field? There was a magnetic field because we're moving charges and you get all of this. Moving charges gives magnetic field. Was there an electric field in that situation?
I would say yes, but I don't know why. And since you asked the question,
yeah,
then it might be no. But that doesn't make sense to me.
Was it because it kept cancelling out it didn't matter in the direction we were looking at it, or something like that, right?
Say again?
Like when we were doing it, in the direction we were looking at, it didn't matter. Like it kept canceling out all the time. I think, I don't remember if that was what we did. I can check.
Something cancelled out.
Well, like
What I mentioned 2 days ago was, if you have a current going through the wire, then the current is the same everywhere. And then I was blanking on the word for circuit. Schakeling, Dutch. Yeah. And I made an argument why the current should be the same everywhere. That was one of Kirchhoff's laws, by the way, of electric circuitry. That the current in a series circuit is always the same everywhere. And that's the reason, right? It has to do with the strength of the electric force, the electric repulsion between the electrons. They have a pile up here. They make sure that they smear out. That was the idea. You're referring to, Stephanie, a different situation than my actual question. My question is there an electric field? And then your argument is something more psychological. You say, so look at my face, hear the tone of my voice, the fact that I'm asking a question, and then you make the conclusion. The answer is probably no. It's probably a trick question or something like that.
Well, I don't know. I would say the fact that there is a... Oh wait, there's no current in there.
In this particular situation, no.
I would say no.
No electric field? Why?
Well, it makes sense that, like, if you now have
an electric field when there is no current going.
Mhm.
And in the previous example, we had a current flowing and we had a magnetic field. It makes sense that we didn't have an electric field then.
Okay.
Yeah, because it's the presence of an electric field that makes a current flow, right?
The charge are always emitting electric field, so it doesn't matter if they're moving or not. Charge itself.
But if they're moving, they produce a magnetic field. Oh wait, but you said in the lecture that when you move charges, you still have the electric field. You just add the magnetic field with the movement.
Yeah, and that was the argument that I used for that was mostly based on energetics. That somebody has made the charges move, put in extra energy, so there is ample energy to make this new thing called the magnetic field. It doesn't go away from the electric field, right? There's no energy loss or energy gain that you get energy from nothing or something. Somebody has moved the charge, and somebody, I forget who it was, but somebody just mentioned, well, there is some outside the electric field maybe that's making the charge move in the first place. That is probably true. That's where the magnetic field comes from. There is a magnetic field, or an electric field. There's many ways of seeing this. First of all, suppose that there's only one electron in the wire. So it has a very, very small charge density, right? It has the one electron in this infinite wire. You know that this one has an electric field. It's given by this law here. Right? Gauss's law. And if I were to put another one here, two electric fields. Now, why, for what reason, if I would add more and more electrons, all of a sudden you would cancel out fields?
Yeah.
That's one thing. And the second argument, again, is this energetics argument. You can make this magnetic field, if they move, without taking away from the electric field. Anyway, long story short, yes, there is a charge, an electric field. Now, the exercise is built up in such a way that the wire is infinitely long, so it's exactly the same as the exercise we did 2 days ago with the magnetic field. You have pieces of wire everywhere, we call that dl, and the amount of charge that there is in a piece of wire dl, that amount of charge they call lambda. There's that. And they say that amount is the same everywhere. Now again, you could have already reasoned that for yourself. The argument that I used, that you can have no pileup, doesn't just apply to moving charge, it also applies to stationary charge. Unless, of course, there's some outside mechanism going on that's keeping more charge here and there. Maybe somebody bolted them to the wire or something like that. But given that they can freely flow and distribute themselves, you will have the same lambda at every piece dl. Okay, so there is an electric field. So that's good. Question is, how much electric field is there here? And that's something we have to calculate. We've already sort of done this exercise. Just replace E by B, and we've already done it. So it's probably going to look somewhat alike. But maybe just out of physical intuition, the electric field is a vector, yes? So it points into a direction. What direction would it point in, do you think? No calculation, just feelings.
Directly away from the wire. Away. Which way? Away. Because the field lines go from plus to minus, right?
Well, yes, well, yes, there is some ambiguity there. The exercise never states whether these lambdas are positive or negative numbers. I just automatically assume that they are negative because we're talking about wires and electrons, I guess. I mean, that's the first thought that comes to mind. The exercise never specifies it. So let's indeed assume that they're electrons, in which case, yes, the field will probably point inward in this case, right? The field points towards where pluses are being pulled. So it's some inward, but how much inward is it? Does it go like this? Not just for this piece. I mean, I'm sure for just this piece it goes over there. But generally speaking, for the whole wire. Immediately downward, is it perpendicular to the wire?
Perpendicular.
Yeah. Why? It's just an intuition question.
Is it an infinitely long wire?
Yes.
So when you add it all up, then you can see that the horizontal cancel out on the opposite sides, and you're left with the verticals.
I think that's a good argument, yes. I mean, yes, this piece of wire would pull it this direction, and if you have this other piece of wire on the other side, the same distance, it will pull in that direction, and if somebody pulls me downward among both arms, will probably go straight through the middle, if the amount of pulling is the same amount. And it is because it's the same charge everywhere. So the only component that survives, right, the components along the wire, parallel to the wire, cancel each other out, but the downward does not cancel out. So it will probably point downwards. That's one argument, right? It's sort of half mathematical because you're thinking components, which is correct because it's a vector, so it does have components. But maybe there's a somewhat more physical or female intuition kind of argument, maybe.
Is there?
Oh, you tell us. I mean,
I haven't noticed it.
It's not like we would know.
How would I know?
Well, I mean, one property of female
just
intuition that probably
assume-
applies to women, but
You're just assuming genders here.
oh,
Well,
yeah,
tell
you
me
should be
what-
careful with these
tell me
things
what I
these
should.
days.
Tell me what I should know. Tell me. Now I want to know what it is.
Okay. Well, let's make it gender neutral. A person's gender
No.
intuition will probably be something like
Like
this.
UCM approved.
Suppose that it would have a direction, right? Suppose that it points towards this point in the line. Now, the situation that we start out with is completely, symmetrical, for lack of a better word, right? There's no difference between this piece of wire and that piece of wire, so why would there be a specific part of the wire where everything would be pulled towards? Just the fact that the wire is the same everywhere means that there is no specific point on the wire to which things can be pulled. So the best thing you could come up with is that it's just being pulled towards the place where the thing already is. That's sort of like an intuitive kind of argument. Now, of course, if the wires were not infinitely long on both sides, yes, then there's probably some direction at some point. Right. So our assumption is, or our gender neutral intuition is, it points downwards toward the wire, I guess, right? Just as a side note, just a question to think about maybe over the weekend or Cardinals break. Why do you never hear anything about male intuition? It's always female intuition.
Because there is no
Okay, be careful. We agree to be gender neutral here, okay?
Then there is just intuition.
There's this intuition, okay. Okay, well, we can just calculate this because it's a vector law that we have here, so that means that everything about the electric field should be built in there, including its directionality. So if our intuition is right, then this thing should know about it too. Which of the ones are we going to use? There's three that relate charges to charge densities, maybe to electric fields. All of they're equivalent. You can use all three of them. It's just which one is the best for the task at hand.
I would say the top one.
Okay.
Yeah, because we're looking for the electric field, right?
Yes.
Yeah. So
Well, this is exactly tailor-made for our situation, right? I mean, we have been given an amount of charge, or charge density maybe, and what we're looking for is this one. You can also do it by these, but then you have to rebuild these divergences. Right? Pry the electric field out again. This one just is tailor-made for the situation. It gives you the electric field, and that's what we're looking for. So let's use that one. E at position R, this is our position R in space, is equal, according to this law, to charge density. Again, note the nomenclature, the notation for the different arms. 4 pi epsilon 0 R in this direction, and then integrate over the volume. That's just our law. Not extremely suitable for the situation right now, is it? I mean, the law is, in the fact that you put something in, you get out what you're looking for. It's just what it requires of us is a charge density, the amount of charge per volume. Well, we don't have volumes here; we have a wire. So maybe it's a good thing to just rewrite this a little bit in such a way that it becomes not an integral over volume, but just an integral over line. dl. What would happen to the charge density here? This is the amount of coulombs charges per unit volume.
We know we have the line charge,
Yes.
so we can just replace that.
Yeah, exactly. Correct. It will be something like this. Now, there's multiple ways of seeing this. First of all, not the milk teeth joke, I'm being serious now, by intuition. because this rho and this dv will just give you the amount of charge in total. So if you want to rewrite this as a similar situation, but now for this one, you would also have to have a combination of this thing and that thing such that gives you the charge in total. Well, obviously that's the amount of charge per unit length times the length. So you can just tell what it is by intuition, say. You could also do by dimensional analysis, because this is per cube, right? Times cube. So if you replace this by times meter, then this should be charge divided by meter, which is exactly what we called lambda before. One final way of doing it is by being a little bit more puristic about it. You say, well, dv is like a dv dl times dl, right? Some sort of Jacobian, maybe. Change the integration variables. Then you ask yourself, how is this one related to that one? And then you say something, well, this one is rho. No, it can be much easier. This is the third. This is meter. dl. This should be meter squared. I'm not really sure where I'm going with this argument, by the way. But it sounds so logical when I started to write it down.
Yeah, I think you should add both the line charge and the
Yeah.
density.
Yeah, you're right. I mean, I'm just doing a bit dimensional analysis here. That doesn't work. Of course, I have to put some stuff in there. It's probably something like this. Some dl, rho times dq or something like that. Right? Yeah. So that's it. I'm not going anywhere with this argument. Forget about it. Try to be clever and puristic, forget about it. It's the correct expression that we have here. I'm going to cut this out of the YouTube video, by the way. We'll never get to 900 with these crappy arguments like this. Anyway, in all seriousness, this is of course how to do it. Okay, so one thing we do know, this lambda goes outside of the integration because it is constant. It has the same amount of charge everywhere, every line element. So we have a whole bunch of constants that just go outside of the integration. That's something like this. And what we end up with is just this. And I guess we're now back in familiar territory because I think the magnetic field exercise looked like this a little bit. Draw a picture for a second. There is a piece of charge here in this part of the wire. The distance from where we are looking to where that thing is well, the vector is called r. A unit length of that vector is r hat. And the total amount of distance of this thing is called r without the vector. Well, you can see that all the properties of this vector, its direction and such, and its magnitude, depend on how far away this piece of line is from your origin. I made an assumption here that I hope to still recognize from a couple of days ago when we did a similar exercise in case of a magnetic field. I originally started with saying, well, here's the origin of the situation. This is the z-axis, randomly called as z. I think this we call the y. The x-axis is the y-axis, something like this. Yeah. And then I said, you know what? Might as well just put the origin exactly below the point that I'm interested in. You don't have to, but it does make the exercise a lot easier. You're free to choose your origin. Obviously, you can choose in such a way that your mathematics comes out easier. So we're going to do the same assumption here. Here is our origin of our coordinate system. Here's x, here's y. Now we should be able to write down this vector now in terms of these coordinates. Right, that's the idea. This is a vector. We should be able to write down the components of this vector in terms of all these things that we have now on the picture, and we can actually do the integration. So before we continue with this exercise, maybe it's a good idea to make some sort of a dictionary that relates the z's and the y's and the x's to capital R's. Vector R has an x component, a y component, and a z component. You tell me what the expressions are for the three components.
X is 0.
Yes, because we've chosen our coordinate system in such a good way that it happens to be 0. Again, you don't have to. Feel free to rotate the whole system in such a way that now y sticks out. So part of your distance has now become x. You will get the same answer, but of course this is much more easy. So yeah, that's 0. Thank you.
Y is going to be S.
Yes, this is where we happen to be standing. We call that distance S. The exercise is to call it distance S.
And Z is going to be Z.
Yeah, exactly. The z component of this vector, the z component is just the distance from the origin to that piece of line. So we call it z, or z, depending on your country of origin, I guess. Okay, so that's the vector. But the Gauss law requires us not just to have the vector, but the length of the vector, a unit vector. This one does not have length 1. And our law requires us to put in one with the hat, the one with length 1. So we might have to multiply everything by something to make sure that the length of this resulting thing is now length 1.
Square root of s squared plus z squared.
Yes. This right. It's this thing that tells you what direction it is, and it's this thing that tells you that it has a unit length. And we need the unit length part. That's good because we also need the total amount of length. Well, that's this number, of course. So r squared, what we're also going to need is going to be z squared plus s squared. So we have a dictionary now. We can relate our capital R to the s's and z's of our picture. So we should now be able to write down the answer to this integration. So let's plug our dictionary into the equation here, or Gauss law. These are 3 equations, by the way. 3 integrals. One for the x direction, one for the y direction, and one for the z direction. So we have to do 3 integrations. One of them is going to be particularly simple.
So that's the X one, right? That's
Yeah, it's 0. I mean, we're just going to add zeros together. Well, that gives a 0. That means, by the way, that the electric field will not point in this direction. I guess you could have guessed that by your gender neutral intuition, right? I mean, there's probably not going to be any. Okay, so that's good. And let's be honest here. The y one is also going to be 0, isn't it? We can do the integration, and we will, just to show that it actually follows from the physics. But maybe via some other argument that you already can tell, well, you know what? The y is also going to be 0. It's not as obvious, because, well, obviously it's not 0 here yet. But I promise you that the answer will be 0, but maybe you can already tell why that is. Sorry?
Because if the net field points in the y direction, then you should have an E field in the y direction.
Not sure I understand that argument.
That one is to calculate the electric field in the y direction, right?
Yes.
And we said that there should be a field pointing into the wire,
Yes.
just in the y direction. So how could there be?
Oh,
You mean that EZ should be 0?
yes, actually, I did mean z. Yes, I'm sorry, just mixing up my coordinates. Yes, thank you. Okay. So, if you were worried that you didn't understand, you were right. I meant it right, said it wrong. It's the z direction that will be 0. But why? So this is going to be 0.
isn't that because all the components of the electric field are going to cancel each other out?
Yeah, that's that argument again that we started out with.
Pointing this way and this way.
Yeah, exactly. That's what I meant by symmetry argument. I mean, that's exactly before we did the exercise. They said, well, just out of intuition, would it have a z component? And then everybody said, no, probably not. And again, it's symmetry. Somebody's pulling on your arm that direction with the same force in the other direction, so this direction will cancel out in total. So this will be 0, and this will be something else. Well, it's not as obvious, but maybe if we just do the remaining 2 integrations, this one and that one, just to see that it happens. So we know it's true, but let's put a question mark as if we haven't calculated it yet. Let's do the z. 1 over r squared, and r squared was z squared plus s squared. And then we take the z component of r, this one, so that's z, but careful now, this of course comes with, so it gives you 3 over 2. We're only looking at the z component of r, which happens to be z itself, and then of course we integrate over the whole wire, so that's a z. So this is the integration. That's the one we have to do for the z direction. This should give you no difficulty. How about this? I'm doing this real time, but I think it's this. Of course, don't even worry about the minus 1/2. I think it's there. We're going to show that it's 0, so this minus 1/2 is not going to change that, but sure. We can do a cross check. If you take the derivative of this thing with respect to z, you should get this back. Derivative of 1 over square root gives you 1 over that thing to the power 3 over 2. That's here. The chain rule tells you, but you have to multiply it by what's inside, which is 2z. That gives you exactly that z, but you have to cancel out that 1z with 1/2. There's a minus sign there as well. That has to do with the fact that you're doing a 1 over. But again, don't worry too much about this part. We're just going to show that it's 0. So regardless of what's here, it's going to be 0. Question, is it 0? We still have to put in the boundaries of z. We're walking all the way along the wire with our z's. Starts at minus infinity, goes to plus infinity. Minus infinity, plus infinity. 1 over infinity squared, sure, square root, 1 over infinity gives you 0. You have to subtract from that the lower boundary, which is minus infinity, but 1 over minus infinity squared will also give you 0. So in total, this is just 0, which is exactly what we knew should come out. There's that. So that's good. And finally, the y component, and then I think we should have a break. Well, almost the same integral. Skipping this factor for a second here, going to put it back in a second. This part is this one, s, and because of the r squared here, what we get is this thing in the denominator, but another one comes down, gives you again 3 over 2. Gives you z squared plus s squared, 3 over 2. And the s I already put there, and of course you have to integrate over dz. That's the one. Now the s of course goes outside of the integral, because it's not an integration variable. So really the integration that we end up with is just this one. Now, Chai and I actually had some email conversation about that because he found a nice way to solve this integral by a nice substitution. Now, the object is not to show how Chai got there. It was a good way. A couple of days ago, we had the same integration with magnetic field. Setup was different, but it happens to be the same integration. So we can just use what the answer is. A couple of days ago. I do advise you, by the way, to just try to look up, or try to find a way to do this integration. There's no physics involved, it's just mathematics. But the answer is this. I'm plugging all the constants back in. Constants are left out for shorthand notation. A little sloppy there being now. Gives us z over s squared plus z squared square root. It's the same one that we used 2 days ago. The magnetic field situation. Plug in minus infinity and plus infinity, subtract them from each other, see what happens. Now, Louis a couple of days ago said, well, it's infinity over infinity, which sure looks like it, right? There's an infinity here and an infinity there, here, but they cancel each other out because this infinity goes infinity to the power 1. This one is infinity to the power 1, so they cancel each other out. And what you end up with is lambda s 4 pi epsilon 0 1 over s, just like 2 days ago, s squared. That's if you put in plus infinity, do the minus infinity as well, and that gives you another 1 over s squared, but now with a minus sign. And the rules of integration tell you that you have to that you subtract these two numbers from each other. So there's two minuses, gives you a plus. And ultimately what we get is lambda 2 pi epsilon 0 1 over s squared and s cancel each other out. So if I'm not mistaken, this is the answer. 2 pi epsilon 0 s. Oh, being very sloppy here. Putting everything back in here. The constant was still already here. This is the full vector. That's the answer. Any questions on the mathematics, maybe? I'm just applying this law and pushing through the crappy vector stuff. Well, if not, let's talk about the physics just for a second. One of them is, we said it was minus, right? Charge density was a minus number. So lambda is minus, right? There were electrons. And that means that the y direction is a minus number. So it points inward, what we expected. The law automatically does so. Again, doing the actual mathematics tells you that there's no z component, just as we expected. Here's an interesting one. It diminishes as you walk away from the wire. You make this distance bigger and bigger, you get less and less electric field. And it goes down, but not as much down as a single charge would go down in electric field. One single charge goes down as 1 over r squared. 2 times further away gives you 4 times less electric field. Yet here, we have 2 times further away goes 2 times less electric field. I mean, it diminishes, but not as much as a single charge. I mean, it's what the mathematics tells us, but maybe there's a physical interpretation to it.
Does that mean it's impossible to fully approach a wire? Because if you do the integral underneath the area of the 1 over r, it does not converge.
Well, I very much agree with that. This expression tells you if you really get that close to the wire, your electric field blows up. There's some issue there, by the way. Right? It goes to infinity if s goes to 0. Yeah, what's the answer to that question, maybe? I mean, if you have an infinite electric field, then you would also have an infinite amount of force. Or, Newton's second law, an infinite amount of acceleration. Now, I've touched wires before in my life. I've never been pushed away with an infinite force. Okay, I'm not a charge, sure, okay. Suppose I was an electron or a proton or whatever, I would probably not be pushed away with an infinite amount of So what goes on there?
That's because the wire is infinitely long.
Yeah. How's that an answer to the question? Just be sure that we have the
That
same.
was an answer to
yeah.
what you just said, not the actual question.
Okay, and then my question was.
Like if you were the
Yes.
proton
Oh,
and
yeah.
you touch the wire, you wouldn't have experienced infinite force because
Yes.
that wire isn't infinitely long, right? So it's like a different.
Oh well, sure. Okay, well that is true. No, that is true. I mean, our setup is not very physical. We don't have infinite amount of wires. Is that the argument?
Kind of.
Yeah, but unfortunately, the going to infinity of the electric field is also there for single charges already. So it's not a property of the wire, apparently. In fact, you could even argue the wire is not as bad as a single charge because this one goes to infinity even more than the infinite wire.
Could it be that since it's an infinite wire, the Z components cancel out, but the Y components, like the actual electric field, adds up, and therefore you've got a larger electric field?
Oh, you know what? That might actually, I think I understand that argument. It might be true. Yeah. The way that I thought of it was this. If you get closer and closer to the thing, then you sort of feel less and less of these. So, same argument the other way around. If you go further and further away, you start seeing more and more of these electrons, right, in the rest of the wire. So that means going more and more up, you get more and more of these parts of wire that you're so all of a sudden start feeling. When you feel them all the times, but you see more of these all of a sudden. So the amount of electric field, it goes down because each and every part goes down, but it goes up a little because you see more and more pieces of wire. And these two effects don't exactly cancel each other out, but they make the amount of diminishing less.
Wait, how's that? Can you repeat what you just said? Then how that's different?
So by symmetry, the Z components cancel out, like lengthwise, cancel out, but you still get the Y components from all the other, for every single part. But those don't actually cancel out. Just cancel out the Z, not the Y. So if it's infinitely long, then you will have more strength.
Yeah, okay.
Like I feel like it's just like you concentrate all that power, maximum power, but all the energy in one point that will give you the vertical line.
Yeah, I think I agree with that. Yes. Yeah. I mean, the final and true answer, of course, is all just written in mathematics, right? I mean, this is what comes out. But we do have some sort of intuition that this is probably true. Okay. Okay, now we've done the same exercise now twice. We've done it for the magnetic field, we've done it for the electric field. In fact, we can just import this electric field on top of the magnetic field exercise that we've already done, because we already established that the magnetic field that we had does not stop this one from existing as well. So at the moment that we start getting these charges to move, we would still have this vector, and on top of that, the one that we calculated 2 days ago. And where does the other one come from? Again, energy, that's you, the guy pushing these electrons through the wire. So we have a full understanding now, I think, of the whole thing, the whole electromagnetism of it, this infinite wire. So that's nice. That's good. Okay, I propose break. It's very easy to go over time, I've noticed. Can we get some coffee? When I get back, I would really love to show you where this last piece comes from. And then we have a full Maxwell equation understanding, so that's good. Okay, we'll just reconvene in a couple of minutes.
Just walking home from wherever they woke up.
Yeah.
Should we continue?
Yeah.
The exercise that we just did could have, of course, been done in a much more easy way, right? To do all this crappy calculation, just like the magnetic exercise, where ultimately this was much easier. People joke and less say, well, you have 1 minute to do it, and we did it in 1 minute because it really is that simple. Same thing here, we use this one, not wrong. It just so happens this one is also easy. So, one line exercise. This was the idea. Electric field, there's a piece of charge lambda for every part of the wire. How much electric field is here? According to this equation, what you have to do is enclose your situation in some area, integrate the electric field over the area, and what it gives you back is the amount of charge that you enclosed. Now, let's do it in the following way. Let's enclose the wire by a cylinder. Okay, and make the cylinder some distance L long. Cylinder. Then that equation, the third one of the electric ones, tells you, okay, well, integrate over the cylinder, what it gives you back is the amount of enclosed charge. Now let's start with the right-hand side first. How much charge is enclosed by this cylinder? If you know that every piece of the wire gives you lambda.
Lambda times L.
Yeah, exactly. Lambda times L divided by epsilon 0. So there you go. So that's right-hand side. Left-hand side. We know something about electric fields, right? Namely, given a fixed distance s, and knowing that electric fields don't care about angles, for a fixed distance s, this is a fixed number. It only depends on the distance, which is fixed in our exercise, it's s, and the angles it doesn't care about in the first place. So you can just pull it outside of the integration, it's a constant. We don't know what the constant is for a given s, but it is a constant. So we get this. And we now have to just integrate over the surface of the cylinder. Now the surface of the cylinder circumference times its height. So it's this circumference times the height. So it's L times circumference to pi times radius. Our radius is called s. Now these two should be equal to each other, so it gives us that E times L times 2 pi s should equal lambda times L divided by epsilon 0. Clean up a little bit. We get a lambda divided by 2 pi epsilon 0 s. That's what we had before. Same expression.
That was easy.
Yeah, it's really just a matter. So, moral of this story: make sure that you pick the right one. They all work, and I mean, I fully agree. This one feels the most natural. It gives us exactly what you want, given your starting position. But in this particular case, still, this one happens to be somewhat easier. Subtleties. So, same expression. 1 line, 2 line exercise. Some subtleties. First of all, the rule says it should be a closed integral. If you recall from 2 days ago, you get this expression. This one from that one we're using the divergence theorem of vector calculus. The divergence theorem only holds for closed surfaces. This one is not closed. I've only integrated over its sides, not its caps. So I'm not doing this circular part here. It's not closed. Is it still correct? Yes, the answer is correct because it happens to give you the right answer, but sure we can do better than this. Suppose we never did the calculation in the other way, so we have no cross check. Somebody could come along and say, wait a minute, wait. Not the closed integral, so you cannot trust this expression.
It works if L is large enough.
Sure. I mean, there's an L here, there's an L there. If it's large enough, well, you still have the caps, right? I mean, even a very big cylinder still has caps. How about you just make it infinitely big? There's no caps at a cylinder that is infinitely big. There is no endpoint where you have to calculate the cap off. You say, wait a minute, can you just infinitely big, make this thing infinitely big? Yes, you can, because L's drop out anyway. You're allowed to take any number, quote unquote. Or, be more puristic, take the limit of L goes to infinity. Okay, well, the L goes to infinity because there's no L in there. It doesn't change the outcome. So, there you go. So that's nice. One other subtlety, there's vectors here, and all of a sudden there's no vectors here anymore. It's a vector integral. The outcome is a number because it's an inner product, and the inner product of two vectors gives you a number. Yet in the calculation, I dropped the vectors within the integral itself, as if we're not integrating over a vector anymore, we're just integrating over numbers. So I'm a little bit sloppy there too.
They always point in the same direction.
They do, yes. But how does that answer the question?
So then the dot product just turns into multiplication.
Yes, exactly. You might know from your vector calculus, or just from your definition of a dot product, A dot B is AX times BX plus AY plus times BY plus ACZ, times BZ. But it's also the same as the length of A times the length of B times the cosine of their mutual angle. An areas always have a direction, and the direction of the area is perpendicular to the actual area. That's just the definition of area, vector area. And yes, we know that this one points outward, so points perpendicular to the area of the thing. So that means that we can replace this inner product by just their lengths, so we're dropping the vectors now, times the cosine of these two. And the cosine is 0, because they point in the same direction. Not the cosine is 0, the angle is 0, so the cosine is 1. So this is why that is allowed. So, much more easy. Okay, now for the big conclusion of today. Let's write down what we already know. We have this one. This is Gauss' law. We have this one. Not sure how to name that one. What you can also prove, and it's an exercise I encourage you to do, that if you take the inner product of this equation, no physics involved, take not the inner product, the divergence of this thing, of B, where for B you substitute this thing, and you play around with this cross product and this divergence, you will find that the answer is 0, regardless of how much charge there is. So this is just a direct mathematical result of this rule. This thing is the second Maxwell equation. The Gauss law is the first one. We also have this one, which I claim is not entirely correct yet. And there's a fourth one, and I just gave you that one as an experimental fact. You can just stick to that for now. But by experiment you can tell that this is true. This is the third Maxwell equation. So we have all 4 of them now. The first one is just a rewrite of this experimental fact. The second one is a rewrite of this experimental fact. The third one, I'm just going to call an experimental fact. And there's a fourth one, which is just a rewrite again of this one. Yes?
I thought that last one should be 0.
Which one?
The one you just wrote.
This one.
Yeah. Or I may be wrong, but that's
I gave it as an exercise.
Sorry?
As an exercise, it said this is 0.
Yeah.
But the exercise said in case nothing is moving, in case the charges are stationary.
Okay.
And here's the answer to that exercise. If the charges are stationary, you will not get a magnetic field.
Yeah.
So there it is. Yes. So thank you. You've actually solved one of the exercises for today. So there you go. You can also do it in a more explicit way, by the way. You can also just take this electric field, take its curl, so actually doing this operation on this thing, go through the actual calculation, and you will find that the only way that this is non-zero is at the moment that, the only way that it's zero is at the moment that this thing does not move in time. You can just go through the calculation. But yours is a much faster way, of course. So yeah, let's be very clear about that. One of the exercises was show that this is zero, but only if things are stationary. Okay, so 4 Maxwell equations now. Again, repeating. Rewrite of this experimental fact. This one is a rewrite of this experimental fact. This one is a rewrite of this experimental fact. And this we just call an experimental fact. So they're all just experimental facts with some rewriting in between. Now, one of the mathematical exercises at the beginning of today, I said, well, there's a reason I'm asking you to show that this is always zero. Always, regardless of what f is. It's simply because it's a mathematical truth. It's not because of physics. I hope you have no trouble proving this for yourself. We can very quickly do it. The rotation of this f is ddx, it's ddz of fy minus ddy of fz. Right, this thing itself is a vector, so it comes with 3 components. What I'm writing down now is just the definition of the curl. ddx of fz minus dz of fx. And then there's dy of fx minus dx of fy. Just the definition of curl. Feel free to check me, by the way, it might be wrong.
Looks different.
Let's see.
So I had was it ddy of fz minus dz of fy.
Where did you get that from?
Book.
Book. So it has ddy of fz.
Yeah.
Well, that's an overall minus sign. I'm sure that this is correct, by the way, so we can check. But I mean, for my argument right now, it doesn't matter. We're going to prove that it's zero anyway. But it is good to check for ourselves. I think this is correct. But feel free to check. In the meantime, Kai, if it's okay with you, let me just continue with the argument
sure.
here. Now we have a vector now, and we have to take the divergence of this. And as you know, the definition of divergence is that you take the x derivative of this thing plus the y derivative of this thing plus the z derivative of this thing. It's some rewriting, takes a while, but ultimately it's this. The ddx of the x component plus the dy of the y component and finally the dz of the z component and I hope you can immediately tell that it's going to be zero. First of all, it's going to be a number, it's not a vector anymore. We've taken all of these things, added them together, so it gives you a number with some derivatives. But here, for instance, you have the dx, dz of fy, and you have the dz of the x of fy. So these two are just the same thing, right? Here you take first derivative with respect to z, and then with respect to x. Here you take them first with respect to z, x, and then with respect to z, but second derivatives don't care whether you do one derivative first or the other. So this one gives you exactly the same thing as that one, except for that one minus sign. So these cancel each other out. That holds for all of these terms. Every one of these terms, if you switch derivatives, and you're allowed to by mathematical means, will find a companion that will cancel itself out. Giving you ultimately that the answer to this one is just really zero. Here, one more. Dy, ddx of fz. Oh, look, here it is. Ddx, dy of fz with a minus sign. Cancel each other out. And there you go. So that's that exercise. So that's true.
Yeah, so the thing that I found,
Okay.
you can see it here. That's right. When I did the calculation at home, that's right.
Okay.
They do have a different notation than you do. For some reason, it's still.
I think you did F cross nabla instead of nabla cross F because it's right. Did I mean
You're exactly right. Kai was right. Yes. Yeah, you're right. You're right. I sort of mentally switched these two around. Your expression is correct. The only difference that it is an extra minus sign over the whole thing. So for the people at home, all of these should have an extra minus sign. Look it up in your books and such. Thank you. But it's still 0. Okay, so that's good. Another exercise done. Now, knowing that this is always true, we can look at our 4 experimental facts in their rewritten forms and check whether they actually hold up. Because we have 2 of these curls, and each, if you take divergence, should, by this mathematical rule, give you 0. Now my claim is this one automatically does. And we can check immediately that that is the case. Because what we have here is the curl of the electric field should give us minus the derivative, time derivative of the magnetic field. It's called Faraday's law. And it's going to take the divergence of both sides. Now we know, we just proved that exercise, that this should give us 0. If right-hand side does not give us 0, there's something wrong with our physics, because physics has to obey the mathematics. Mathematics triumphs over physics here. I hate to admit it, but it's true. And this side, well, here's a spatial derivative. Here's a temporal derivative. Those don't feel each other. You can just easily switch them around. Gives us this. Just as a mathematical fact, you're allowed to switch the spatial derivative by the temporal derivative. And this is 0. It's not even the derivative itself that is 0, it's even more stringent than that. It's this thing already by itself that is 0, let alone its derivative. Why is it 0? Because of this law. Why was this 0? You could easily prove from this law. So apparently, this Faraday law is in complete agreement with this law. So they're not contradicting each other. So it's good. 0 equals 0. Well, that's probably true. Now for the curl of the magnetic field.
Wait, can I ask one thing? If you take one step back, where you, if you go a little bit right, go right.
Right, okay.
Where you have the triangle times the b.
Oh, yeah, here, yeah. Mm-hmm.
So if we didn't know that that equals 0,
yes.
How would you still prove it?
Well, that's an interesting question. In fact, I might make it an exam question or something like that. Now, you know now what I'm going to ask, okay? Suppose that you didn't know about this one. That's your question.
Yeah.
But you know by mathematical rules that whatever comes out here should be 0. Mm. It's an interesting question whether this is enough to prove that this law must hold. I think the answer is no, though, because you could also have that this is just a constant.
Like to me right now, it's just like that thing is 0 because this law says it's 0, and then that law is 0 because that law says it's 0.
No, it's not as simple as that. No. Because no. My point here is this is really not trivial. Nature could have been built up in such a way that this were not true in the following way. This rule is an experimental fact. This is also an experimental fact. But this one is a standalone experimental fact. Has nothing to do with this one. And this one is just a rewrite of this one. Right? If you take divergence of this thing, you will find that it is 0. Yeah. So what I'm saying is this law and this law are completely separate from each other. They hold true regardless of each other. So the fact that they combine together to form something that is also true is not trivial. Okay, we're going to calculate the rotation now of the magnetic field. Well, we know what the answer is. It's over there. Again, this was experiments tell us. But just as here, we have a rotation, so that means if we take the divergence of that rotation, it should give us 0 yet again. Music. So this is 0 because of this exercise. My claim is this is not 0 in of itself. There's multiple ways of seeing this. One of them is in the following. Use a little bit of physics. A notepad here. I'm going to write down something. You see if you agree with me. What I'm going to write down now might look a little random, but if you think about it for a second, you might agree with me. Do you agree with it that this is true? Just read the physics that's written there, not so much the mathematics.
Yeah.
Yeah, tell me.
Do amperes relate to time?
Yes, it's charge
It's
per
charged per
time.
time.
Okay.
So in that sense, by dimensional, and this is what you're going for, I think, but for dimensional reasons, you can tell this too. This is ampere or charge that flows through per unit time through a volume. And then you take its derivative. So what it should give you back is the amount of charge per volume as a function of time, which is exactly this. So dimension-wise, it's correct.
Why the minus though?
Yeah, that's my question to you.
Oh.
This physical interpretation, what does this mean, right-hand side?
Rate of change of charge density over time.
Yes. So I'm standing here and just looking around me how much charge there is per cubic, and I find that 2 seconds later it's become a smaller number. Okay? So that's what this says. And this equation that says, oh wait, but that's equal to this thing. What does this mean physically? It's a spatial derivative of the current. Because that's what it says, right? This thing here, divergence really is a complicated way of saying spatial derivative.
In all possible directions.
In all possible directions, yes. Or, as I put it 2 days ago, hand-wavily, it's how much current is sticking out. Standing over here, look around how much charge I see disappearing per second. That's what this says. And here it says, oh, you know, that's just the spatial derivative of the current. Does that make sense? You can hear by the tone of my voice that I hope that the answer is going to be yes. But intermediate step. What does a spatial derivative mean physically? What does ddx mean?
Gradient.
No, that's just another word for the same object. What does it mean physically? You're right. It's not a gradient, by the way. Gradient is how you turn numbers into vectors by derivatives.
Gradient.
Distribution.
Oh,
I saw that.
yes? No,
Velocity. Speed.
sorry?
Speed.
No, that's over. That's the.
That's
that's
over
the
this time.
Oh, over there.
Well, generally speaking, a derivative just means how much this object is changing over some sort of other observable. Now, if it's changing over time, you get a speed. How much is a number changing
Is it
per
like-
unit time?
Is it like curvature or something?
Not curvature. I have this object here, charge density. And a second later, I find that the number has become bigger or, say, smaller. That's a temporal derivative. I wait 1 second, 1 moment in time, and I see how much it has changed. A spatial derivative means I'm not changing the amount of the moment in time, and I'm looking again. I'm changing space. I'm standing over here. I do 1 step to the side. How much is the current now here? How much has that changed from place to place? Not from second to second, but from place to place. That's what this says. So that's just really just an interpretation of what derivatives mean. Going back to the physical question, I'm standing over here. I find that if I wait 1 second, a piece of charge has gone missing, has moved away. It's not here anymore. Yeah, it must have gone here, right?
Yeah.
Literally what it says here, the amount of charge that you see missing at one place in time, you can find back by stepping aside and find that it has apparently moved away from you. That's what it says. If you think about it for a little bit more, then you understand that this is the conservation of charge.
Yeah.
If you find the charge is missing, it must have moved away through space. Now, these types of equations appear very ubiquitously in physics. It's called the continuity equation. It simply means you cannot just have stuff disappearing without it having moved through space. That's what it says. I'm going to demonstrate this equation right now. I have a piece of charge, okay? Okay. There you go. Did you notice that 1 second I was here, next second I wasn't anymore? That's because I moved through the door. I changed in time the number at this position. It's because I moved through the door. That's what it says, because I moved in space. By the way, conservation of charge is this equation is more stringent than this conservation of charge. I could also just teleport myself to the other side of the door. I would have had conservation of Gideon, because at any moment in time there is the same amount of me in the universe. But this one is a little bit strong. It says not only do you have to have the same amount, if it moves from one place to the next, it must have moved through space. So teleportation it's an anti-teleportation equation. That's what it says here. Given that we know this, look what we have here. Yeah. Take the minus sign outside. So what we do 0 minus. So what we've done here, we've plugged in that charge not only is conserved, it must move through space if you see it disappearing. Suggestions at this point? Well, given the amount of time, let me do it. I have a derivative with this of the charge density, but I also have an expression for charge density somewhere in my already existing equations. It's a ddt of charge density.
No, you can replace with that one.
Yes. So if we do that, replace this by Maxwell's first equation, you get that's electric. And divergence of the electric field. You get this. So there's a little bit of rewriting here, but it's still physically exactly the same thing. You get this. It should be 0, but it's not. The only way that this is 0 is either if there is no electric field, or it's a constant electric field. But this must hold generally, not for one specific situation where the electric field happens to be constant. In fact, if you have a magnetic field, then you know that there's a changing electric field somewhere. So you already know this cannot be 0. So this is not working. Something is off here. Not equal 0. Should be 0. Conclusion. This equation, what we started out with, and this equation that we plugged in do not match up. They screw up your mathematics. So that means that either mathematics is wrong or one of these equations is wrong. Then Maxwell, the scientist, came up with the luminous idea. Let's do the following. Apparently, this is wrong, but what if we add something to it that if you now take the divergence, then this new stuff that you've added cancels out exactly this part. So let me rephrase that. So you can parse as I say it. Let's add this thing. Will give you this expression, should be 0. So add something to this, that if you take divergence of this new part, the divergence of this new part will cancel exactly this full expression. What should I add? Take the divergence of this thing and this extra part here, its divergence should cancel exactly this. Add something. That something should not cancel this thing. The divergence of that something should cancel that thing.
The curl, if the divergence of the curl of something is 0, then
Well, yes, but if I were to write a curl here, any curl, then taking the divergence of left-hand side would give me 0. Then this one would give me 0, and I would still have my problem. So it's good comment because it means whatever we're going to write here is not going to be a curl.
So mu naught, epsilon naught, delta E delta T.
how did you come from that?
Because if you take the
Go ahead, go stand so for everyone to see, including the people at home. Here, take
so if you take the divergence of this whole thing, you need to write it down too, but this is a constant, so that's going to go outside. And if you take, then it's basically the divergence of this thing times this thing. Go over here. So what you get is
Do the same thing.
yeah. And then they cancel out, and then it's 0.
That's it. This is why I said I'm going to say it again so you can parse it. And maybe now, in retrospect, you fully understand what I meant by that. I said, write something here that its divergence cancel exactly that divergence. Well, there you go.
Feels kind of arbitrary though. It's like, oh yeah, let's just add this so
It is arbitrary, but it's not arbitrary because this thing is not arbitrary.
yeah.
Hi.
Oh, wait. Am I in the right place?
Yeah, you are, but we're about to.
The wrong time.
Finish, almost finished.
Yes.
Oh, wait. Sorry.
That's fine. Okay, so we really have to do this.
Huh?
I thought it was an tutorial.
No,
Yeah.
I think you
Yes.
use as
Right
the
place,
replay.
wrong time.
Yes.
2 hours late.
Space time.
Okay, just let me finish up for a second. So, again, experimental fact, experimental fact, experimental fact. Experimental fact does not agree with mathematics. So yes, you have to add something, and you can say, well, that's arbitrary, and in a sense it is, because I'm sure there's multiple ways of adding something to this that will cancel that one out. So it's up to experiment to decide whether this is still true with this add-on, and apparently it is.
So that's been confirmed experimentally.
Yeah,
So it's
absolutely.
lit. Right,
Yes.
that's funny. Okay.
Yes. There is something you can say about this because you can add other stuff that will make that different. In fact, one of the lectures we're going to talk about, so after the carnival break, is I'm going to show you that there's multiple ways of writing down the same equations that even though they look mathematically different, not in this way, but actually adding new add-ons to the field of this type, you would always still get the same physics, the same experimental results. It's not the same as rewriting from here to here. I'm actually saying I'm adding extra electric field and extra magnetic field, yet I get the same physical pushing and pulling of charges and currents. It's called gauge. And it's the second lecture of this series, but after carnival break. Now, these four now, first Maxwell equation, second Maxwell equation, third Maxwell equation, and this one with the add-on is called the fourth Maxwell equation. And when I was a student following this for the first time, I remember this very well. It was in 2000 that I had my first lecture series in Electrodynamics. That the teacher, professor giving this lecture series, he said, well, now we call these four the Maxwell equations. As well, that's crappy, because this is by Gauss. This one is a rewrite of Biot Savart, right? These are all scientists, Gauss, Biot, and Savart were two separate scientists. This one is Faraday. And this one is again the original was still a rewrite of Bio Savar. And now Maxwell comes along after 200 years, adds one thing, and all of a sudden all four of them are named after him. that's a crappy situation, but yeah, but that's the case. These, by the way, these four are exactly the ones that I posted in my qualitative PowerPoint on the Maxwell equations. And yes, they're completely experimentally confirmed. Yes?
So, I don't understand what is like the physical meaning of the argument we just added.
Well, in my PowerPoint, I made at some point I said, well, there's four equations, and this one means this one means that. So let's go over that one more time. Maybe then everything will click into place, having seen all this. This one just says the amount of electric field that sticks out depends on how much charge there is, which I guess makes sense. Here's the amount of magnetic field that sticks around, apparently is 0. All that goes in has to come out again. This one just means you can make an electric field by shaking around a magnetic field. And this one is interesting, because note that the original second Maxwell equation just says that the magnetic field lines should stick out as much as they stick in, but it doesn't say what they should look like. If they stick out in some angular shape or via some onion shape, it just says the amount in should be the amount out. So this is not complete. It's missing something about how the field lines look. If you will, it just gives you boundary conditions. Whatever they look like, they should come back. It doesn't say how they should look. And that's what this one does, because it tells you, well, how they should look is given by this first term. The amount of charge, current, tells you in what direction they would go. And just like the also equation tells you, you can also make magnetic field, not by charges, one step, sorry, mix up my words here. Again, this one just tells you the boundary condition for magnetic field lines. The amount in is the amount out. It doesn't tell you what they should look like. The first term does here of this one, tells you, and they should look like this. But as you know that electric fields can also make magnetic fields, there's a second term, that's what this one says. Yes. In a sense, it looks very random to add this part to it, just to make this work. But for some sort of stupid symmetry reason, you would also expect it, right? I mean, if you know that you can make electric fields by shaking magnetic ones around, wouldn't you expect that magnetic fields can be made by shaking electric fields around?
But isn't that idea already captured in the fact that we're using J, which deals with moving charges and therefore intrinsically deals with changing electric fields?
Yeah, that's a good question. Because of course this thing already is some sort of moving charges, right? So there's a question there whether separating them as two different entities isn't just some arbitrary rewriting, maybe.
But it doesn't work if you just have it as one, right? Which is
No, there's no. Apparently, just writing it as one of them apparently is not any different. So that's true. Maxwell realized this, the scientist himself. I mean, the question is very well put. Maxwell himself realized this. He called this actually a current. He called it the displacement current. He says it acts as if there is a current. It's really just like this thing. So in a sense, you agree with Maxwell here. There's really not a difference there. But apparently mathematics wants you to have these things as separate entities. And I'm thinking out loud whether there's an actual physical reasoning behind that, apart from it has to follow. And I think that there is. But I'm thinking out loud now, so what I'm saying now might be wrong. This J here, no, I'm not sure. I'm not sure. I wanted to go in a certain direction, but I'm not sure my argument holds. It's a good question, though. Now we will have to think about it, I guess. I mean, the question is clear to everybody, I think, yes? Okay. Well, we have a carnival's break to think about this. Long story short, we do have the four Maxwell equations. After carnival break, I'm going to continue with these, add some extra fields to it, see if we still get the same physics, and that allows us to rewrite everything in different terms that does not include magnetic fields and electric fields. Anyway, that's something for after carnival break. Now, there's more exercise than we actually have time to do in the tutorials. As I said, just find for yourselves the solution manual. I had no difficulty finding it. The ones that we haven't done, feel free to try them. It's all the same type of reasoning. The gist of it we've done from beginning to end. The rest is just exercising yourself. If you have any difficulty, do let me know. Send me an email, or we can talk about it after carnival break. And that's it. So, thank you.